Right, so we are now looking at this example. Um, and the example says, consider the fixed point iteration given there. Show that this iteration converges for any x naught in the interval. How many iterations the theory predict that it will take to achieve the accuracy? Okay, so this says uh, we have two parts. The first one, show. In the question, we have two parts. Show that this converges. Right. First of all, we want to identify our g. So we identify our g. So our g of x is on the right hand side, just 1 plus e to the power minus x. Remember, for it to define an iteration, we need to show our I here is equal to what? 1, 2. So we need to show that g of x, the range of g of x is actually 1, 2. Now, if you look at this function, let's look at g prime of x. We want to check the range here. This is just minus e to the power minus x squared. So g itself is a decreasing function. So you get the maximum at the lower end point and then the minimum at the upper end point. So g is decreasing. So the range will be easy to find. So if you take g of 1, this will be equal to 1 plus e to the power minus 1, which is just 1 plus 1 over e. So this is less than 2 also, but greater than 1. So g of 1 is greater than 1. G of 1 is greater than 1, but less than 2. And then we go g of 2, we also have 1 plus e to the power minus 2, which is 1 plus 1 over e squared, which is less than 2, but greater than 1. So we now see that g is contained in this interval for all x that are in the same interval. So it says g maps this interval to itself. So therefore we can now apply the fixed point theorem, because we now know that g is, and of course g, so we now know 1, and of course g of x is continuously differentiable. So we now know these two properties of the hypothesis of the theorem for existence of a fixed point. So now we want to show convergence. If you show convergence, you are just saying the absolute value of g prime of x, okay, which is actually the absolute value of minus e to the power minus x, which is just e to the power minus x, or 1 over e to the power minus x. And of course, this is a decreasing function, so you can test here that the absolute value of g prime at the maximum should be at 1, is less than or equal to g prime of 1, which is equals to 1 plus 1 over epsilon. This is equals to 1 over e, which is less than 1. And take note that so therefore the fixed point point iteration converges for all initial points that you can pick here in this interval. Doesn't matter where you pick it, but take note, by finding the maximum here, we then now know that OK is 1 over E. So we now have the maximum, and OK is 1 over E. And it says here how many, so that's the second one, how many iterations does the theory predict it will take to achieve 10 to the power minus 5 accuracy? So all you need to do now is to go to the error bound formula. So the error bound formula, we now know that alpha minus xn, the absolute value, is less than or equal to k the power n of 1 minus k times the absolute value of x1 minus x0. So now here you have to, you need x1, x0, and x1, and it's not specified here, but we know that it converges for any choice that you can make inside there. So all you need to do now is to then say, okay, let me choose. Let us choose x not to be equal to 1. It's very convenient to choose that one. And then you now know that your iteration is 1 plus e to the power minus xn. So you need x1, which is equals 1 plus e to the power minus x0, which is equals to 1 plus e to the power minus 1, or 1 plus 1 over e. Okay, so you will know that x1 minus x0 is 1 plus 1 over e minus 1, which is just 1 over e. So it's very convenient here. All right, so so even if you take the absolute value, it's the same. All right, so we now have x1 and x0 and k. So what we want now to solve is k to the power n over 1 minus k times the absolute value of x1 minus x0. E should be less than 10 to the power minus 5. All right, so that's the inequality. So we're now saying 1 over e to the power n over 1 minus 1 over e, that's 1 minus k, times 1 over e is less than 10 to the power minus 5. Okay, so let's see what it gives us. So here you will have 1 over e to the power n over e minus 1 is less than 10 to the power minus 5. Can you confirm that that's correct? Or even rather, we can even have this one as 1 over e to the power n, e minus 1 times e to the power n is less than 10 to the power minus 5. Or you can now simplify and say, multiply that side by e to the power n. Okay, so you then have e to the power n is now greater than now 10 to the power 5 over e minus 1. Okay, then you then use natural logarithm. So n times ln of e is greater than ln of 10 to the power 5 over e minus 1. So n then is greater than ln of 10 to the power 5 over e minus 1. So we need to calculate this. value and see. Let's see what it gives us. So the we want to calculate this value. Let's see how it comes out. So 10 to the power 5, the log becomes 10.9716. So this is 10.9716. So it says n is the integer or the natural number that is greater than 10 to the power. So then n would be equal to 11. Okay. Then n would be equal to 11 in this case. So you need 11 iterations of the fixed point theory to actually um, get a convergence of 10 to the power minus 5. All right, I want to add another question here and then say, now what okay, this one we should say find the error bound after 6 iterations. After 6 iterations, find the error bound or calculate the maximum error that you incur after 6 iterations. So you then now say xn plus 1 is equals to 1 plus e to the power minus xn. So now we are generating, so we have now a x1 x naught is equal to x naught is equal to 1 x1. We have seen that it's so x1 was equal to 1 plus 1 over e, which is 1.36788. If you continue computing, x2 is equals to 1 plus e to the power minus 1 plus 1 over e, and so forth. You then get 1.25465. X3, continue, it will give you 1.28518. X4, if you continue, it will give you 1.27660, and then X5 will be 1.27898, and then X6 is then 1.27832. Okay, so after 6 iterations, then n is equals to 6. So we are worried that we want to determine the error bound of approximation here. So remember, our error bound is alpha minus x6 is then less than or equal to k the power 6 over 1 minus k times x naught minus x1 minus x naught. Okay, so then we are just computing this right hand side. We know k is 1 over e, and the x1 minus x naught absolute value, we saw that is 1 over e as well. So then this would be equal to 1 over e to the power 6 times 1 over e over 1 minus 1 over e And if you compute properly, you should get 1.44258 times 10 to the power minus 3. So this will be the error bound of approximation after 6 iterations. And you can now appreciate that once you have the error bound, you can use it to calculate one, the number of iterations to reach a certain desired accuracy, or two, you can actually compute the error bound after a specific number of iterations. So this is how you can use the fixed point iteration to estimate its errors. Okay.